Okay, hi everyone. How are you? Hopefully, this recording will be absolutely Oscar worthy. And so, what we're going to talk about today is a continuation of our conversation about sums. I want to show you two sums that come up frequently, and this is going to be something that TIC saw last year. AB, you may or may not have worked on this last year, though I think you would have. I mean, it's part of your section. It's in one of your sections in your textbook. But what I want to talk about here first are these two sums, okay? So we know a couple of things in terms of shortcuts, a couple of shortcuts. So for example, right here, look at this right here. This just right here is the sum of the first n integers, 1 plus 2 plus 3, okay? This is the summation notation version of this open sum. Some sums have what are called closed forms associated with them. Some people like to call them these formulas that give you the sum, right? The two sums that I want to show you that have closed formulas associated with them are the summation from k equals 1 to n of k and the summation of k equals 1 to n of k squared, okay? And here is the open form of that sum. So when we say that the summation from k equals 1 to n of k equals n times n plus 1 over 2, what that means is we're being given this wonderfully convenient formula. So for example, if I wanted to calculate the summation from k equals 1 to 75 of k, one way to do it is to literally list out 1 plus 2 plus 3 plus 4 all the way through, okay? Grab a calculator and start adding up all those terms. As you can imagine, that's incredibly time consuming and, in my opinion, an utter waste of time. Because we have this closed formula that associated with this sum, we are able to find the sum very easily. So because n here is 75, the summation from k equals 1 to 75 of k will equal none other than 75 times 75 plus 1 all over 2, or 75 times 76 over 2, or 75 times 38, and this equals some number here. I don't have a calculator on me, but if you do, go ahead and just find that, okay? So again, not all sums have closed formulas associated with them. In fact, very few do. The reason why I bring you back to, or I reintroduced this one and this one is because we're going to use these below. So this sum, summation from k equals 1 to n of k squared, has this closed form, okay? One of the things that I remember is you may have done this exercise at some point in some like math class early on. You may have kind of done this little puzzly question, which is like the summation of, right, the sum of the integers from 1 to 100. And some of you may have seen that if you actually add here, this is 101, right? 99 plus 2 is 101, 98 plus 3 is 101. And what you have, you get 50 pairs of 101, 50 pairs of 101. And so really this sum, the summation from k equals 1 to n of k, has been kind of a puzzle that's been kind of bandied about and thought about for quite some time. And at some point, and it was actually using an exercise like this, it was discovered that, oh, this is a lovely closed form of a sum. Okay, what this leads us to is here, okay? What I'm going to do here together with you is evaluate this definite integral, the definite integral from 1 to 3 of x squared dx. Here's my rendering right here. Okay, and I went and kind of shaded this net signed area, given the interval and given the function that is above the x-axis. I do know that at the end of the day that this net signed area is going to be a positive number, And now below, I just kind of walk through very methodically all of the things we've done so far with Riemann sums and definite integrals. So I just found the width of each rectangle, which is right endpoint minus left endpoint divided by n, the number of rectangles, right? N is the number of rectangles, don't forget. So the width of each rectangle is 2 over n. Then right here, I generate an expression for what the kth right endpoint would be. And of course, the kth right endpoint, again, this is all from a reiteration from yesterday's class. It's a plus k delta x, or a plus k delta x, because a here is 1 and here's delta x. Then I write down the height of the kth rectangle is f of the kth right endpoint. And then all I do here is just substitute this 1 plus 2k over n into my function, right? F of x is x squared, and here I have that, okay? And then I have the area of the kth rectangle is, of course, width, right, times the height. And then to the right here, you'll see I just do some algebra, namely squaring this binomial out. And yes, okay. Then next line here is I generate the expression for the sum of all n rectangle areas, and the summation of all n rectangles areas is right here. Okay, it's right here, right? Summation from k equals 1 to n. And then I go all the way through, and here's my kind of final climactic moment. I add this statement: the limit as n approaches positive infinity of the summation from k equals 1 to n. And notice here my very deliberate use of this now equals the definite integral, because I involve the limit now, right? Once we involve the limit as n approaches positive infinity, we can say that it does in fact equal the definite integral. If I had wanted to make a relationship or generate a relationship with the definite integral of this step, I would say this is approximately equal to the definite integral from 1 to 3 of x squared dx, because there is no limit here. There's no limit right beforehand, right? Okay, so here is where, everyone, this is where the story now picks up, okay? So everything up until now has been old news. I think the only thing that could have been new news is just this above here, these two sums, and in particular the closed forms, but that's a revisit for the most part, okay? So here we go. We're gonna now go through and continue. So from here, everyone, let's first look at the summation for a second, okay? Notice something. Do you remember in class how I talked about if the summand has a factor that does not involve that which is changing integrally, which is k, we can take that 2 over n and just pull it through, right? So this then becomes the limit as n approaches positive infinity of 2 over n times the summation from k equals 1 to n of 1 plus 4k over n plus 4k squared over n squared, okay? I'm going to make it clear now that this is the summand. Okay, now let's go ahead and flesh this out. The limit as n approaches positive infinity of 2 over n. Okay, so what I'm just going to do, just for the purpose of clarity, is just make it very clear that I want to just kind of flesh the summation out quite a bit. Now look here. The summation of a summand that involves terms, or in other words, the summation of a sum, right? Because addition is commutative and associative, I can rewrite this with the order of addition reversed. So, in other words, what I'm saying here is if you have a number of objects to add, it doesn't matter the order in which you add them. And as I work through this question with you, I'm going to reiterate something that I say all the time, which is often the most difficult thing about calculus is the algebra. And this exercise here is going to demonstrate that completely. All right, everybody, now I want you to take a look at each individual sum. Look at each individual summation here. Pull over to the side here. When you have the summation from k equals 1 to n of 1, let's walk over here for a minute. Summation from k equals 1 to n of 1, guess what this equals? This just equals, well, 1 plus 1 plus 1 plus 1 plus da 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 da. What's the last term going to be? It's going to be plus 1. How many ones are you going to have here? You're going to have n ones, right? Or in other words, you're going to have n times 1, which is just n. All right, wonderful. Well, this allows us to now come down here. N plus. All right, let's look at this sum now. I want you to notice something. Do you see the 4 over n? I'm going to pull the 4 over n out of the summand and tell me why. Yes, correct, because 4 over n is a factor of the summand that does not involve that which is changing integrally, which in this case is k, okay? Plus, same thing here, summation, in this sum, I can pull out 4 over n squared times the summation from k equals 1 to n of 1 over, goodness gracious, I'm getting way too over excited here. My mouth is like wanting to run forward. Very good. Now, I wish I knew what this equaled. I wish I knew what this equaled. Guess what? We do. Those two sums have these wonderful closed formulas. We have an expression. We know what we can do there. Okay, let's put that in. So now I have the limit as n approaches positive infinity of 2 over n, all of that times n plus 4 over n, okay, right here, this is important. We know this equals n times n plus 1 all over 2 plus 4, I'm going to use color, gotta do it right, 4 over n squared, and we know this equals n times n plus 1 times 2n plus 1 all over 6. And can you believe it? Look what we've done. We have now dealt with the summation part. We've dealt with the summation piece of this limit of a Riemann sum. I've dealt with the summation piece of this limit of a Riemann sum, which is really no easy task, as you can see. Now I'm in familiar territory. How is everyone feeling? How is everyone feeling? Good, I hope? Good, or good in air quotes? I'll take either. All right, everybody, let's take a look at this. The limit as n approaches positive infinity. I think what I'm going to do here is I'm going to take this 2 over n and I'm going to distribute it in here. Distribute it in. All right, maybe I'll meet you there. Maybe you're someone who's feeling really well oiled right now and you want to just pause me and see if you get there on your own. And or maybe you're not. It's up to you. Okay, I'm going to be now down here, okay, plus, what do I have? What is going on now? I've got, let's see, 4n times n plus 1 times 2n plus 1 all over 3n cubed. Did everyone see how I kind of simplified the 2 as I distributed? All right, very good. Here we go. Well, let's see. The limit as n approaches positive infinity of 2 plus, okay, maybe we're saying to ourselves, you know what, we've taken such great care, let's just write this all out just because we know we can. Okay, come in. Hi, who is that? Hi, Allison. Hi, Allison. Say hello to yourself because I'm doing your screencast right now. So, Allison, say hi.
Hi.
Hi. Okay, it's going to feel so weird. You're saying hi to yourself when you listen to this. All right, here we go. Limit as n approaches positive infinity of 2. This just equals 2 plus a limit to infinity right here. Limit to infinity of a rational function. We look at dominant terms in the numerator and denominator. If they are the same, we take the lead coefficient. So it's going to be 4 over 1 or 4 plus. This is going to be limit as n approaches positive infinity. Again, we have a rational function. This is just going to be 8n cubed plus dot, dot, dot over 3n cubed plus dot, dot, dot. So this is going to equal 8/3. We have just evaluated the limit. I'm going to do a quick little finding a common denominator here. 8, 12, 20, 26 over 3. And ladies and gentlemen, what have we just done? We have just found that the area, come with me, this area right here, that area, we found it exactly. It equals 26 over 3. This equals the definite integral from 1 to 3 of x squared dx. Okay, now you can go and do your homework.